Hello everyone, my name is Nicholas Wiley. What we're going to be doing today is we're going to be using the Crank-Nicholson method, which is an implicit differencing method, to try and model the temperature profile of our bar. Now, in the previous video, we encountered some problems with specifically our code, but more than that, with our model using explicit differencing. And what we found was that delta t could not exceed, could not exceed 0.5, and we proved that using the von Neumann stability analysis. Now what we're going to do is we're going to use the Crank-Nicholson method and implicit differencing to try and figure out a better way to model our temperature profile of our bar. And using this, we're not going to have that limitation of having it less than 0.5. Quick important note, which I will probably mention multiple times throughout the video, is that when you do increase your time step to a lot larger values, you run the risk of having less accurate results. But other than that, let's get into this. So what I've gone ahead and done is I've gone ahead and written our partial differential equation, and I'll just erase that now. You've seen that plenty of times now in the past couple of videos. And I've gone ahead and I've written this up here. Now you may be asking, Nick, what have you done up here? So what I've gone ahead and done is I've included this part of our equation, and I've also changed this according to what the Crank-Nicholson method calls for. Now what does it call for? What it calls for is we are going to be analyzing not just at the current time step, as you can see we have right here, the j plus 1 comma n, j comma n, but what we're going to do in addition to that is we're going to use the next time step to analyze this. Now this is again going to help us with our results and making sure that we don't have that limit that we did before at the t is less than or equal to 0.5. Now, in addition, it is an average, so we have alpha over 2. We have to average these values, and that's the whole point, the whole driving force of what we're going to be doing. So we're going to have this average right here, and what we're going to try and do is we're going to try and clean this up. It's going to become a little bit messy in a couple minutes, but I just thought that I'd get this out of the way. It's a lot of algebra, so I decided I'll just cut it and get rid of all the algebra. No one wants to watch me rewrite all of this, but all I did was I used this equation that we had before, and then I added with the next time step, and then we average that with the alpha over 2. Now, an important note to make about this is that we have this alpha over 2 term, and what can we do? Well, if we look at this side, we can put this delta x squared in the denominator. So I'll go ahead and erase that. And also, sorry, let me get rid of this one. So that already looks a little bit nicer. So we have this alpha over 2 delta x squared, and we can also get rid of this delta t term. So we'll have alpha delta t over 2 delta x squared. Now this may look familiar to you because it is familiar. This is going to equal our r term over 2. Also, if I didn't say anything about it, alpha is our thermal diffusivity, our delta t is our time step, and then our delta x is our position step, if you'd like to say that. But we're going to denote this as, for the rest of the video, we're going to call this U. So I can go ahead, do a little bit more erasing. We have this equal to U. Now, Nick, you may be asking, Nick, what are we going to do at this point? Well, what we're actually going to want to do is we're going to want to separate these different time steps onto the left and right sides of the equation. Now, what I'm going to do is I'm actually just going to make a quick cut. I'm going to have that all laid out for us, and then we'll keep moving with this. I've gone ahead and cleaned up our equation, as you can see. I've moved all of the time steps forward, n plus 1, if you'd like to say, to the left-hand side. I'll just denote this as left-hand side. And then I've moved all of our current time steps to the right-hand side. Now, looking at this, you can see that we have a lot of unknowns here. Now, how many unknowns do we actually have? Well, what we can do is we can actually draw our bar. We can draw all of our position steps. Those are actually pretty close to even. It's the best I've done. Either way. So we're going to have our temperature on our left side, denoted TL, and then we're going to have our temperature on the right side, denoted TR. And at these points, we can call this point 0. This is going to be known for us. We know the temperature, it's 50. And on this side, we know the temperature, it's 80 degrees Celsius. But how many segments have we gone? If you remember, we have that our x is equal to n delta x. So what we're going to denote that is not lowercase n, but capital N. That will be the end of our bar. Now, as I've just said, how do we know how many unknowns we have? Well, every single one of these internal segments that we have is going to be an unknown. So how many unknowns are we actually going to have? Well, we're excluding the left and the right, the 0 and the n, the boundaries, the caps, almost the ends of our bar. We're going to have n minus 2. And that is how many positions that we're going to have to figure out for our bar right here. So I believe that should be about 18 segments for what we have. But what does that mean for us? That means that we're going to have 18 different calculations, 18 different values, unknowns that we're going to have to calculate. Now, what does that mean for us? It means that what I'm going to do is I'm going to make a cut, and then I'm going to get right into our matrix multiplication, which is going to be a little bit ugly, and I'm not the best at explaining it, but I'm going to do my best nonetheless. So I'll go ahead and clean this up for us, give us a bunch of space, because we're going to have very big matrices. So I'll see you in a second. All right, now we're going to move on to the matrix multiplication. Now, I'm not the best at this. I did take a little bit of a refresher course, so hopefully I can explain this to the best of my abilities, and hopefully you can understand. So let's just hop right into it. I'm having a little bit of marker issues, so if there's an unexpected cut, I may have gone to the store to try and buy a new one or something, because they're all dying. I've been writing on this so much. Either way, so the first thing that we can fill our column right here with, nice job, Nick, is going to be our temperature values, which is going to start at 1. As I've said, we're not going to start at 0, and well, I'll just keep going and then I'll explain the rest. So we'll go T1, T2, T3, T3, all the way down, and we'll go to T sub n minus 1, because we aren't going to go to n, because that would be our right side of our bar, which is set to 80 degrees, and we're not going to go to 0, we're going to go to 1, because the left side is set to 50 degrees Celsius. So, looking at this, what can we do? Well, the first thing that we want to talk about, for me at least, is this right here is T sub 2. So when we're talking about when j is equal to 2, we can go ahead and put our eyes right here. And that is going to correspond. Now, first, before I get ahead of myself, this is going to be row column. That's how matrix multiplication works. So looking at this, we can start right here at T sub 2. So when we have j is equal to 2, we'll be at this, we'll be at this term right here. So our first term and our first column will be negative u. Now, moving forward with that, as we move on, we're going to move on to 1 plus 2u. This marker's not too bad as of now. Shook it up a little bit. And then, further moving on, when we have that 2, we're going to get to T3, so that is going to be negative u again. I'm actually going to write these a little bit closer. Okay. Now, the next easiest one that we can probably move on to is this T3 right here. So T3, looking over here, when we put in j is equal to 3, we get that T2 right there. So that's going to be this column right here. So we're actually going to have that negative u. I think I keep pointing to this one. I mean to point to this one, though. So right here, we're going to have negative u. And then here, we are actually going to have the 1 plus 2u, as we are at 3 now. And then over here, what are we going to have? We can have that 4 spot. We can put another negative u, squeeze her in right there. Now, as you can see, we sort of have a pattern emerging. Now, if we look up to here, we have T1. So what are we going to have? We're actually going to have this term right here. We're going to have 1 plus 2u. And then what are we going to have next for our T2? We're actually going to have negative u. And then we're going to actually have a little blank right there. We're going to have a few blanks right here. Now, this is very convenient for us. And this is pretty much the full extent of where we need to go, because we've realized that we do indeed have a pattern, which is very nice. I actually forget the name of the pattern. It's blanking in my head. When we go on to Python and get into there, I can try and explain a little bit better, use the term, explain what it all means. I'll actually probably have a picture of this and then explain how we're actually going to code this. We're going to be using a neat new Python function for this. I believe it's through SciPy algebraic, linear algebra, maybe? Algebra? It's something like that. Which is pretty neat. We're going to learn a new function, try and explain it to the best of our ability. But either way, so now we have our left-hand side, and then we have our what we're going to be multiplying it by. So now what we're going to do is we're going to move on to the right-hand side. Now, what are we going to do with this? I think it's actually pretty easy for us to start with T2. Now, how are we going to start this? Well, the first way that we can start is we're going to plug in n equals 2 for right here for our first term. Now, what we're going to do is we're simply just going to plug in 2 into our first terms. What are we going to end up with? End up with ut3. This one's going to be an even more obvious pattern for us. So now what we'll do right here is we'll have the 1 minus 2u term here, and we'll have t2, and then what we'll have left is another u, and it's going to be t1. Marker's dying. Uh-oh. Hopefully we can keep going through this. At least get to the end of this matrix part. So moving along, what we can go ahead and do is we can move to T3, and following this pattern, all we're going to do is we're going to add 1. ut4, 1 minus 2u, t3, and then we're going to be left with ut2. Okay, now where things start to get interesting is at this t1 and this tn minus 1 term. So looking at this, if we're going to follow our pattern upwards, we're going to have ut2, we're going to have 1 minus 2u multiplied by t1, and then what we're going to end up with is ut0 over here. Now, I'll explain why that's important in a second, but first let's get to this tn minus 1 term. So moving all the way. Apologies for the random cut. One of the roommates accidentally set off the fire alarm, and my face went bonkers. Had to figure that out. So we're actually back. If I remember, I'll put it in for a blooper. It's a pretty good moment. But either way, what were we talking about? We were talking about this term right here, tn minus 1. So coming over here, what we're going to have is we're going to have u, and so since we're at n minus 1, we're going to be at ut sub n, and then we're going to be at 1 minus 2u, t to the n minus 1, and then we're going to be at u t to the n minus 2. Now we have two terms, as I've said, that we really need to worry about is this t sub n and this t sub 0. Now these are already known. These are solutions. These are already known. They're solutions to our equation that we already know. Now, since these are solutions and these are already known, what we can actually do is we can combine these two terms right here. They both are at t sub 0, and as I've said about 5 times, they are both known. So what we're actually going to do is we're going to add both of these together. What we're going to end up with is we're going to end up with ut sub 0 plus ut sub 0. And so it doesn't matter for the time step where we're at. These are both going to be equal no matter what because it's t sub 0. So what we can actually do is we can make this a 2u t sub 0. And if you couldn't see it coming, what are we going to do down here? For the same thing, we know our temperature at the end. So what we can do is we can make that another 2u t sub n this time. So with that, I think that ends our matrix. I'm going to get ready to go into the Python coding. I'll try and get a few things ready so that it'll be more easy to explain once we try and go through this, because it can get a little bit complicated when we talk about a banded matrix. But either way, I'll see you in a minute. All right, hello everyone, and we are on the computer now. What we're going to do is we're going to be looking at we're going to be making a Python code for the Crank-Nicholson method, implicit differencing for our temperature profile of our bar. Now, hopefully I don't have too much already on here. I do not. Okay, that's good. So what we have is we have our matrix that has 3 main bands, and that's going to be the main thing that's going to be driving us. The whole point of this is that we have a banded matrix with 3 bands that are non-zeros, which we have right here, right here. This is going to be our main band, and then we have this right here. This is our matrix that we had. It's not a very good format, but it works. It'll work for us, at least. And then what we also have is we have a little screenshot. Since this site does not want to work for me, I don't know why. If you have any suggestions, let me know. I've been having this issue. But either way, so this is what we need. This is rather what we're going to be using. We're going to be using SciPy linear algebra, solve banded. So as you can see, we're going to be talking about our non-zero lower upper diagonals. Then we have our main diagonal, all of this. So the first thing that we should discuss is our indexing. So let's look right here. So this is the shape that we are going to be having, and we have this right here. This is going to be a 0, 1. Now what is that going to correspond with for our indexing for our matrix? Well, if you look, this is in the 0th row and the first column following Python indexing. Just add 1 to those and it'll make sense. So if we look up here, we're talking about the 0th row and the first column. So that's going to correspond to negative u. Now that we have a little bit of the indexing understanding, we can go ahead and talk about this. Okay, let's go ahead and pull this up. And luckily I don't have too much down. Now I've already gone ahead and I've changed our R value that we had. Quick background. This is from the temperature profile of our bar for explicit differencing. And what we can see is we can see how unstable this is, and hopefully at the end of this process we can have a large time step, which I've already had and gone ahead and added. And hopefully this will be stable even with that large of a time step. I'll go ahead and change this while we're at it. All right, so moving along, what we can do now that I've explained this, actually I don't know if I have, we changed the R to the U. We had the R before, and then as I said, all we have to do is divide that number by 2, and then we get U. A little bit of a rhyme there. Now we can go ahead and do is we can set up our matrix. So what is this going to look like for us? Lowercase a is going to be equal to np dot zeros. Now how many rows and how many columns are we going to have? So for our rows, what we're going to do is we're going to count how many bands that we have. And of course we have the negative u, the 1 plus or minus, I always forget, the 1 plus 2u as our second band, and then for our third band another negative u. So we're going to have 3 there. And then what are we going to have for our columns? Well, we're going to have how many unknowns that we have. So how many unknowns do we have? Now that we have, if we have 20, we're going to do 20 minus 2 because that's how many we have in the middle. So what we'll say is we'll just keep it as n minus 2 for ease of access. Now we need to go ahead and include our bands into our code. Now that we have our A, which is our array set up, we need to include these bands into what we're going to be doing. So the first one we have is negative u, then we have 1 plus 2u, and then we have negative u. Now what is the indexing going to be? First, I'll write this down for us just to give us an easy start. Well, first and foremost, this is going to be going to start with 0. This is going to start with 1. This is going, 0, 0, 1, 2. Or that's just a weird way of putting it. 0, 1, 2. Either way, it didn't really make sense, but it will, I promise. Okay, we're going to have A, and we'll start with 0. I'm going to leave this empty for now. This is going to be equal to negative u. Okay, and then we're going to have A of 1, because this is in position 2 if you'd rather. Position 2, yeah, I guess that makes sense. We're going to have, I believe it's 1 plus 2u. Then over here, we're going to have A 2. Sorry, it's going to be equal to negative u once again. So what are we going to have for the rest? Oops. What are we going to have for the rest of our indexing? Now that we have the rows down, what are we going to do for our columns? Now, if we look at this is actually pretty simple. I think the easiest one for us is going to be the main band, as I've spoken of, which is just 1 plus 2u. I hope I had 1 plus 2u. This is going to be our main band, which means it goes from beginning to end. So we can denote this simply with a colon. Oh, down 1. We can simply denote this with a colon because it travels the entire band. It goes all the way to the end from beginning to end. Then if we look at this term right here, it starts at the first and goes all the way to the end. So what we'll have for this one is we'll have 1 colon. And then for this one right here, we start at the beginning and we go not to the end, but to the one before the end. So what we'll have for this one is we are going to have a colon and then a negative 1 because it's the term before the end. And now we're ready to assemble our entire matrix. What I've gone ahead and done is I've gone ahead and created what we need for our for loop just to save us a little bit of time. And before I go and put it into our for loop, I'd like to explain how we got to this. If we look at this equation right here, what we need to understand is how this is going to work. Why is the indexing like this? Well, looking at this, look at our first column right here. So what we have is we have our start is going to be T2, and it's going to go all the way to N, if that makes sense. So we have 2 until, you could put an N there, but we just have a colon because it will run until it's done. And then in addition, what we have for this column is we have 1 minus 2 times u, and then we also have from 1 all the way to -1. And then for this one, we have from 0 all the way to n minus 2. Now, in addition, what we're going to need to do is we're also going to have to append this value. Oh, I did not do this right. Sorry. This was a mistake I must have made earlier. Hopefully it wasn't too problematic for everyone watching at home. It must have been there at the beginning. I just now realized that mistake. So what we have is we have this right here, and what I meant to say was that we have this term right here. We have this term right here, which we're going to have to append onto our list, but nonetheless, let's just do that now. So let's go ahead and we can copy and paste this into our for loop. Now what we can do is we can call this b. So we'll have b is going to be equal to this, and I sure hope that all of our syntax is correct there. Now what we're going to need to do is we're going to need to add these values. b0 is going to be equal to b0. What we're going to do is we're going to add we need to add u multiplied by t0. And then what we're going to need to do is we're going to have to do the same for the very end of our list. So we're going to have b-1 is going to be equal to, oh, let's just copy this down. That'd be a lot easier. All I have to do is change that real quick. So we'll make this a -1, and then we'll make this a -1, and then we'll make this a -1. And now I think we're ready to do our solve banded. I may do a little bit of cleaning in here just to make sure that everything works. I'm just going to run it through. I'm not sure exactly what I need to take out if I really need to, so I'm just going to finish with it, and then I'll be back in a second. Now we are in the home stretch. Now I've gone ahead and done a couple things in the meantime. I've gone ahead and done is from SciPy WinAlg, I've gone ahead and imported the solve banded linear algebra. In addition, I've also changed this I range to 500, a nice even number. I have double checked to make sure that this is 1. I may have been a little bit ago. I'm not sure if I mentioned, but I also put the initial temperature to be 25. And then I believe all that we're going to have to do is we are just simply going to have to use our solve banded function now. Now, an important thing that we need to notice about this is number one, what we need to input. So we're going to have to input the number of non-zero lower and upper bounds, which is going to be 1, our banded matrix, which will be A, and our right-hand side, which is going to be B, as we've just done. And then after we've done that, I believe that we should be good. So what we do need to set this to, we need to set this to be equal to our inner intervals. That's a weird way of saying it. All of our unknowns, which, as we've discussed, 0 to n, so it's going to be from 1 to -1. We know the two n's, 0 and n, so it's going to be 1 is going to be our first unknown, everything in between all the way up into our second to last term. And then this is going to be equal to, I believe I did this correct. Yes. I wanted to make sure I imported it. Solve banded. And then looking, we need our, I don't know why it says L and U, but we're going to need, lower and upper. I'm a dummy. So we're going to have lower and upper. We're going to have our, what our matrix is, and then we're going to have our right-hand side for that. Now, hopefully, if everything is correct, I'm double checking. I really hope it is correct. I believe that we should be good. Let me make sure that everything adds up. I want to make sure we have a good finish for this. And would you look at that? We have successfully used the Crank-Nicholson method to create this plot that is very resistant to instability, large time steps. Now, another thing to keep in mind, as I've said earlier, is that if you have too large of a time step, your results may become inaccurate. So it's best to just keep it a little bit lower, but now you know that we can do this in a stable way. Now, it's really cool that we use this new solve banded function. I'm not sure if we'll ever use that again. I'd be interested in doing it. I thought it was a pretty neat concept, how we constructed this and everything like that. And other than that, I hope that you have a good day, and I hope you enjoyed, and I'll see you in the next video.